Hello everyone, and welcome to another Chemistry with Mr. Faust tutorial. Today we're going to be talking about energy. In our first example, we're asked how many kilojoules of heat energy are required to raise the temperature of 365 grams of water from 68.0 degrees Celsius to 90.0 degrees Celsius, given that the specific heat of water is 4.18 joules per gram degree Celsius. So the first thing we need to know is our formula for specific heat. And we learned in class that the formula for specific heat is Q, which is heat energy, is equal to M, which is mass, times the specific heat of the material, times delta T, which is the change in temperature. And the temperature can be in either Kelvin or Celsius because 1 degree change in Celsius is the same as 1 Kelvin change. So if we plug the numbers here into our formula, Q is heat energy, M is mass, so here we have our mass. The specific heat of water is given to us right here. And then the change in temperature. Well, the change in temperature went from 68 degrees to 90 degrees. And delta T is always equal to temperature final minus temperature initial. So in this case, the final temperature was 90 degrees Celsius, and the temperature initial was 68 degrees Celsius. So our delta T in this case is going to be equal to 22.0 degrees Celsius. So we have Q, our heat energy, is equal to our mass, 365 grams, times the specific heat, and the specific heat of water is 4.18 joules per gram times degree Celsius, times our change in temperature, which is 22.0 degrees Celsius. So now when I solve for Q, I get a pretty big number, which is 33,565. Now, that's a pretty big number, but the question actually asks us how many kilojoules of heat energy. So we need to convert these joules to kilojoules. And the reason I know that these units are joules, if I look here, grams cancels grams, degrees Celsius cancels degrees Celsius, and the only unit I'm left with is joules. So to convert this from joules to kilojoules, I can remember that there are 1,000 joules in 1 kilojoule. So when we do this now, we get 33.6 if I'm keeping this at 3 significant digits. Rounding this right here at this digit, we get 33.6 kilojoules of energy. The other way I could have done this is by taking our number 33,565 and just remembering how we did unit metric conversions earlier in the year with King Henry doesn't usually drink chocolate milk. And if we're starting with units of joules, that's going to be a base unit. And if I want to get to kilojoules, I need to slide my decimal 1, 2, 3 places to the left. And when I take this decimal and slide it 3 places to the left, we get 33.565, which is how we rounded to get 33.6 kilojoules. Okay, for our next question, we have a 4-gram sample of glass was heated from 274 Kelvin to 314 Kelvin and was found to have absorbed 32 joules of heat. What is the specific heat of glass? So using our formula again, we have Q is equal to M times specific heat times the change in temperature. If I want to rearrange this to be able to solve for specific heat, I need to divide both sides by m times delta T. M cancels out on this side, and delta T cancels out on this side. So what I'm left with is Q over M times delta T is equal to specific heat. Alright, so just cleaning up that formula so it's a little bit easier to see, we have specific heat is equal to Q over M times delta T. So if I read my problem, we have a 4-gram sample, there's my mass, was heated from 274 Kelvin to 314 Kelvin. So remember, delta T is always going to be temperature final minus temperature initial. So 314 Kelvin minus 274 Kelvin. And that equals 40 Kelvin. So delta T is going to be 40 Kelvin. And it says it is found to have absorbed 32 joules of heat. Remember, heat energy we use Q to represent. What is the specific heat of the glass? So let's go ahead and plug these numbers into our formula. We have specific heat is equal to Q, which in this case is 32 joules, over our mass, 4.0 grams, times our change in temperature, which is 40 Kelvin. When I solve this, I get 0.2. And when I'm punching this in the calculator, I need to make sure, since I have more than one number in the denominator, that I keep parentheses around this, or I find the product of 4.0 times 40 first, which would be 160, before I divide 32 by that number. So our numeric answer is 0.2, and if we look at our units, we have joules on top, we have grams on the bottom, times Kelvin on the bottom. And none of those units will cancel out. So the units we're left with are joules over grams times Kelvin. And for units of specific heat, that's what we should end up with. Specific heat by definition is how much energy is required, how many joules of energy are required to change 1 gram of a sample by 1 degree Celsius or Kelvin. So the units that we get for specific heat should be energy over grams times Kelvin or degree Celsius. So this makes sense. For our next problem, we have 3.5 kilojoules of heat are added to a 28.2 gram sample of iron at 20.0 degrees Celsius. What is the final temperature of the iron in Kelvin? And it gives us the specific heat of iron, which is 0.449 joules per gram degree Celsius. So let's look at our formula, which is Q is equal to M times specific heat times delta T. So this is asking us what is the final temperature. So this one is slightly different, where it wants to know what is the final temperature of the iron. Now notice in our formula there's nothing here for final temperature, but we do have delta T, which is our change in temperature. So if we were to solve for our change in temperature, and we want to know how much did the temperature change, we can see that we started at 20 degrees Celsius, and we'll see how much our temperature changes so we can figure out what our final temperature is. So we're going to rearrange this formula to solve for delta T. So to solve for delta T, we need to divide by M times specific heat on both sides. So our mass cancels out on this side, and so does our specific heat. So again, we're left with delta T is equal to Q over M times specific heat. So cleaning up the formula a little bit, here's what we have. So let's go ahead and start plugging numbers into our formula. First, we see that we have 3.5 kilojoules of heat. Now remember, heat energy is Q But this is given to us in kilojoules, and we need joules to be able to use it in our formula. So 3.5 kilojoules, remember kilo means 1,000, is the same as 3.5 thousand joules. But to show our math for that, we need to say 3.5 kilojoules. And I know that in 1 kilojoule, there are 1,000 joules. So we get 3,500 joules. So this is going to be our Q. Over our mass, which is 28.2 grams, times our specific heat. And the specific heat is given to us in this problem, so it is 0.449 joules per gram degree Celsius. So when I solve for this, here's what I get. 276. And here we see that joules cancels joules, grams cancels grams, so the only unit I'm left with is degrees Celsius. So remember, we weren't actually solving for final temperature here. Remember, we were solving for change in temperature. So our temperature changed by 276 degrees Celsius. Well, if we go back and look at our original problem, we started at 20 degrees Celsius. So to find out what my final temperature is, I just need to add that 20 degrees Celsius to our change in temperature. And we see that our final temperature in Celsius is 296 degrees Celsius. So if we ever need to find the final temperature, that's what we do. We just find the change in temperature and add that to our initial temperature. Now in this case, it says that heat was added, so we know that the temperature went up. That's why we are adding 276 degrees to the 20 degrees. If it said that the temperature went down, we would just be subtracting our change in temperature. Now, the final part of this question was, it asked for the temperature in Kelvin. So if I look here and I want to change this to Kelvin, remember our formula is we just take degrees Celsius plus 273 gives us our temperature in Kelvin. So 296 plus 273 gives us 569 Kelvin. Now for the next example, we're going to look at an endothermic reaction. And there are two ways I want to look at this to try to think about what is going on. The first one is what is happening with the system. When we talk about thermochemistry, we're really talking about two parts. There is the system, which is the thing that we are choosing to look at, and then there is everything else, which we call the surroundings. So if I want to know what is going on with the system in an endothermic reaction, I can think of the system kind of like a box. And if this box is our system, everything else around it are the surroundings. So for an endothermic reaction, endo means into. Endothermic reactions are when heat or energy is flowing into the system. So if I think of this as my energy flowing into the system, that is what an endothermic reaction is. Now if I wanted to look at an energy diagram where we have energy increasing here as time increases this way, then an endothermic reaction would look something like this. We would start off with our reactants at kind of a low temperature or low energy, and they would eventually gain energy until they became products. So here we have reactants, and here we have our products. So for an endothermic reaction, how do I get from the reactants to the products? Well, it's kind of like thinking about a ball. If I had a ball and I wanted to get it up this hill to where the products are, what would I have to do? I would have to put energy into that. So an endothermic energy diagram looks like this, where we have to put energy into the reactants to get them to form the products. Now, if we look at an exothermic reaction, it's going to be very similar. We have for our system diagram, the system, which again is just going to be represented by a box. And everything outside of the system is just going to be called our surroundings. So for exothermic, exo we can think of exiting. An exothermic reaction is when we have energy exiting the system and going to the surroundings. So if energy is leaving the system and going to the surroundings, that is an exothermic situation. Now, the energy diagram for an exothermic reaction, if we have increasing energy here, over time, increasing this way, then what we see is that for an exothermic reaction, it looks something like this. Okay. Where we have our reactants here, and our products down here. Now in this situation, we start off with reactants, and it's kind of like a ball rolling down a hill. The ball has a lot of potential energy up here, but by the time it gets down here, what has happened to all that potential energy? Okay, it's left. It has actually exited the system. So an exothermic energy diagram would look something like this. This is like when we combust methane. We have our methane and our oxygen gas up here, and down here we end up with our products, things like CO2 and water. The amount of energy in the methane gas and the oxygen gas is a pretty high amount of energy. The amount of energy in our products, our carbon dioxide and water, is actually lower. So all of that energy has to go somewhere, and that's the heat and light that we feel when we light the Bunsen burner to burn the methane gas.